My name is Guček. I'll be presenting some of our work, as well as the importance of data and computer science and archaeology, and hopefully it'll shed a light on some problems that and potential improvements that archaeology can go towards in the future. First of all, the growing volume of digital data and archaeological documentation opens up new possibilities and opportunities, as well as many challenges in modern archaeology. The need for effective understanding, management, and exploitation of data in the context of archaeological cultural heritage is both emphasized, as well as the need for active decision-making and the formulation of new management strategies and policies. In the 21st century, this is becoming the domain of data science, which requires an interdisciplinary approach, as well as the active use of information technologies and tools to complement passive digital heritage data with both paradata and metadata. In my lecture and demonstration today, I intend to present an example, as well as possibilities of computer processing of digital data of 3D models of a Paleolithic wooden point. 3D models are one of the more important data carriers of archaeological digital heritage. They, as we will be able to see, store an exceptional amount of data and information that can be processed, analyzed, researched, compared, visualized, or even printed according to the needs of the researchers without directly dealing with the original artifact. This is especially important as well as useful for archaeological remains that are either extremely valuable, rare, or extremely fragile and can be damaged simply by incorrect or slightly sloppy handling. For approximately 3 decades, archaeologists as well as digital heritage managers have been asking questions and looking for solutions to credibly obtain, preserve, and document cultural heritage information and data through non-invasive methods and techniques, as well as affordable tools. At the same time, they're looking for solutions on how to comprehensively research, analyze, present cultural heritage data to both the world's professionals as well as non-professional public. On one hand, they are burdened by the high cost of certain new technologies coming to the field, while on the other hand, they are burdened by a tsunami of digitally structured as well as unstructured data, which accumulates usually in a raw form in generally unrelated digital collections. The reality is that the answer to all these questions and dilemmas was already presented in 2007 by the tragically deceased pioneer of cloud data science and computer expert Jim Gray, though some of you may know him as one of the lead researchers at Microsoft. The answer would be, and to all this, is the cloud data science, or as he put it, the fourth paradigm of data-intensive scientific discovery, while the goal would be to have a world in which all of the science literature is online, all the science data is online, and they can interoperate with each other. So let's just quickly go over what exactly he meant by this fourth paradigm idea. Firstly, there are 3 conditions necessary for the realization of this fourth paradigm. The first being trained data processing experts. The second being the development and use of a new generation of scientific computer tools for both the management, analysis, and visualization of larger databases. And finally, the data transfer of upgraded digital cultural heritage to the cloud. So generally speaking, for the last point, he wanted all the models, all the data, all the metadata, all the paradata, as well as the computer processes that would analyze this data to be on the cloud and to be accessible to everyone. So open source, as many would put it nowadays. To summarize, the idea of the fourth paradigm, as we can see on the left figure, is the idea about integration of data processing methods and techniques of said data and computer science, as well as archaeology, which process digital data in the web cloud. This is clearly an example of a new doctrine in digital heritage. So to just give a few more words, this is another sort of example on how the idea would look. A few more words. It's about data science, the methods and tools that we could use, and just to give us a quick refresher. So we have statistics, AI, neural networks, deep learning, software development, and archaeology, providing us with all of the practical knowledge that we require to give quality analysis of the given data. If we were to quickly just look at how he planned for the data science's life cycle in this, it would be at the top the acquisition of data, the preparation of data. So basically segmenting the data, determining the various metadata, paradata, and other parts of the analysis that we want to make. Then based on these initial analyses, we would create certain hypotheses and models that we would test. The evaluation of the data is then the actual testing, whether these hypotheses are coincide with the data we're actually given. After that, we would deploy both our data as well as the processes used to the cloud. Then we would have operations, basically, as I said before, computer computation on the cloud. So everyone could access it, everyone could experiment with it, and basically a type of online peer reviewing system, but with actual tests and experiments rather than simply reading an article. And the final step would be optimization of all the previous steps to basically improve them and streamline the ideas. Now, while archaeology, unlike certain other fields, hasn't really had any particular programs or applications that are specifically tailored to its needs, there are many tools of data science which can actually be used in archaeological research and data analysis. So anything from R to Python to the D3 JavaScript library, SAS, Jupyter Notebook, I'm sure is known to many of my colleagues at the Faculty of Computer Science, as well as things such as MATLAB and Cloud Compare and MeshLab, which we'll see later. To summarize, data science uses both structured and unstructured data. It is scientific in nature and is meant to perform an in-depth statistical analysis of the previously mentioned data. It leverages more sophisticated statistical and predictive analysis, as well as things such as machine learning, artificial intelligence, deep learning, you name it. It also combines historical and current data to predict both past and future performances and outcomes. Two questions, or perhaps I should say two problems, have recently troubled digital archaeology and those responsible for storing and processing cultural heritage data over approximately the last 3 decades, I would say. Firstly, how to obtain and preserve data as well as information on the remains and cultural heritage in a non-invasive way. This was already addressed in the year 1992, and the general idea was to develop and improve non-invasive methods and techniques for both analyzing and conserving artifacts. The second question being how to efficiently and comprehensively store, process, analyze, and publicly present a multitude of structured and unstructured data from different digital databases. This was posed around the year 2011, and the general solutions were 3D modeling, visualization, as well as a standardization of metadata and paradata. So typical stuff for data science. Just to quickly go over, the historical development of what led to data science and archaeology, and which were the, I suppose you could say, key points that called for massive changes. Firstly, both archaeologists and archaeologic informatics approached the solution of the problem over about the last 30 years and have adopted a number of international documents and recommendations. In 1992, being the earliest, at least that I could trace back to, the archaeological profession undertook the Valletta Convention to give priority to cultural heritage data using non-invasive methods and techniques. So, the answer to the first question, which I mentioned before. In about 2003, UNESCO brought digital heritage to the forefront, and 2 years later, the Council of Europe emphasized the need to use digital technology in archaeology and cultural heritage. The 3D model as a data carrier, as well as 3D visualization tool, were highlighted in the original London Charter in 2009. And further, the need for comprehensive data treatment of digital heritage was later on highlighted at the Principles of Seville in 2011. 3D visualization as a more comprehensive tool was then also, I guess you could say, upgraded and further specified during a new introduction to the London Charter around 2012. So, as I mentioned before, I am sure we have no doubt that digital archaeology and the management of cultural heritage need a new forward doctrine. It's also a commitment to the previously mentioned EU recommendations, which require cultural heritage managers to set up a single digital collection of European archaeological and cultural heritage online by the year 2025. So that would be, I suppose, the next big step in digital cultural heritage. So I've already mentioned the main points, but just to quickly refresh. The Valletta Convention focused on non-destructive methods of investigation and for them to be applied wherever possible. The Charter on the Preservation of Digital Heritage in 2003 basically predominantly talked about actually creating digital materials for both analysis and conservation and to give them priority in use. The Convention on the Value of Cultural Heritage for Society predominantly talked about the use of digital technology in archaeology as well as to improve and enhance cultural heritage. The London Charter, its original version in 2009, talked about the use of 3D visualization methods. The Principles of Seville predominantly focused on what I mentioned before, the standardization of both metadata and paradata. And then the new introduction to the London Charter in 2012 further talked about various types of 3D visualization to be used in both communication and cultural heritage. Now, since we've got all the historic stuff out of the way, let's get a bit more specific. So firstly, what exactly would the significance of 3D models for digital archaeological heritage be? 3D modeling is, generally speaking, a non-invasive method as well as technique of digital archaeology which significantly complements digital documentation using 3D models. So it's important to note we can have anything from structured light scanners, photogrammetric methods, laser scanning, computed tomography, MRI, CT scans, you name it, all of these can be used to give us a vast amount of data. Furthermore, we can then process the data using special algorithms and software, specifically designed for, again, processing this data, then further reconstruction, visualization, analysis, or even addition of 3D models. The two main programs that I'll be mentioning are Cloud Compare and MeshLab, which we used in our specific example, which I'll get to in a minute. I would also here like to highlight that we'll be talking about two different versions of 3D models, one being surface 3D models and the other being volumetric 3D models. As for what's the difference, I'll get to that in a minute. Before that, I would like to highlight that 3D models make it far easier and more practical to create documentation of both data, metadata, and paradata, allow us easier processing of all of said data, give us new methods and forms of public presentation of artifacts, be they digital technical drawings, virtual or augmented reality, 3D visualizations or animations, and even things such as 3D printing are here. They also allow us a more comprehensive methods of 3D analysis, be they volumetric, statistical, or graphical. And finally, they give us new and improved options, as well as potentially highlight the current issues that certain conservation processes face. Basically, we can use them to study how accurate or how appropriate a conservation process is for various types of archaeological artifacts. As I'm sure you all know, different artifacts require different conservation processes based on the material of the artifact, based on whether it's metal, wood, stone, bone, and you probably have to also take into account the different types of wood will require different conservation methods. So Now, I mentioned we're going to talk about exactly what a surface 3D model and volumetric 3D model is. So a surface 3D model, as you can see, just shows us the general surface, texture, and potentially even color of the artifacts that we want to look at or that we want to analyze. While they look quite nice from an outward perspective, the reality is that on the inside they are hollow. So while we can do quite a bit of analysis on them, I just figured I'd mention that we can't exactly do internal analysis with them. This is where volumetric 3D models come in, where they're generally considered to be more or less the same thing as a surface 3D model, with the exception that they also have the internal structure modeled. Now, the thing I should also mention is that surface 3D models will usually be in the form of point clouds or meshes, predominantly meshes if you're using structured light or laser scanners, while point clouds, due to, well, them also having an internal structure, will usually only be as point clouds for volumetric models. I already mentioned before the various usabilities of 3D model data. This is just a quick overview, but as I said, I already went through this. So now let's go over our case study, aka the Paleolithic wooden point. I'm sure my colleague Miran Eric has already mentioned it at least, and he was also the one who discovered it. So I'll be going over just the general information about it, just to give you a general idea of why we chose this particular artifact as our point of analysis, I suppose you could say. So the Paleolithic wooden point was discovered in around 2008, and it is considered a priceless piece of cultural heritage since a radiometric study placed it around the age of 44,000 years old. Further redating at Oxford showed it to be about 38,500 years old, give or take a few centuries, which would make it one of only 8 wooden tools or weapons from the Paleolithic era that currently have been found, or should I say that currently exist in Europe as well as the world. The wooden point, which is believed to be part of a Paleolithic hunting weapon, shows us the presence of both hunters on the western outskirts of the Ljubljana moors, and the symmetrical wooden point is made from yew wood, which is particularly notorious for conservation, for how hard it is to efficiently conserve, and was, again, we believe, used by hunters from the time of the decline of the Neanderthals. Now, as I mentioned, the wooden point was discovered in 2008. In 2013, it was sent to Mainz, Germany for conservation using a melamine resin process. From its initial discovery, 5, well, technically now 6, but our initial study used the 5 3D scans were created. 1 in 2009, 3 before, during, and after the conservation process. Those are the 2013, 2015, and 2017 models, and the 2018 model, which was done after the point was returned from Mainz back to Slovenia. The archaeologists that worked with the point, after basically receiving it back, noticed quite obvious dimensional changes, be it the length, width, and thickness of the point, as well as certain changes in the texture. However, in order to more accurately figure out where the changes come from, we decided to do a computer analysis rather than simply looking at it with a ruler and a pencil. So we originally did a volumetric and deformation analysis of the surface 3D models in around 2018, and a further analysis of the point in 2020 after another model was made in 2019. As I mentioned before, this is only one of 8 wooden Paleolithic artifacts found in Europe as well as all of the world, and it can be considered a priceless piece of cultural heritage. Before I go over to the actual models, let's quickly take a look at how the models actually came to be. So the interesting thing is that apart from there being 5 models, they were done using 4 different scanning tools. The first 3 being structured light scanners, the ZS Scanner 800, the ATOS 3 scanner, as well as the ATOS triple scan scanner, while the final point was done using a micro XCT scanner. Now, as you can see, the numbers here show exactly how many cloud points each model had, as well as how many triangular mesh points it had. While these numbers by themselves might not mean much, we can look at we can basically summarize the bottom 3 numbers from them. For every 1 point of the 2009 3D model, the 2013, 15, and 17 on average have 18 points, which means 18 times higher quality. While the XCT scanner done in 2018 has approximately 118 times more points than the first 3D model that was created, and about 20 times as many points as the 3 previous models, giving it the highest fidelity. Since pure numbers might not illustrate what I'm getting at here, I'll give you this picture. So on the right side, we have a picture taken using a camera of the point when it was shown at the museum in Vrhnica for a limited time. And as we can see, pretty good image. You can see most of the details, abrasions, cuts, and so on. And then here we have on the left, on the bottom, the first Z-Scanner 800. We see, most of the greater details are highlighted very nicely, and it's, as I said, very usable in the greater scheme of things. But now compare it to the ATOS triple scan. There really isn't much comparison. Even places that, could be seen as smooth before have a lot more detail now. Now further compare this to the XCT scanner, which gives us arguably an even better image than actually looking at the point. There are 2 things I'm getting at here. First would be that computer vision has the potential to be far more accurate and far more detailed than regular human vision. The second would be that the quality of our 3D model greatly depends on, well, the quality of the scanner, which usually means how much money we spent on the scanner. So, as I mentioned before, financial issues with the 3D scans. So here's another image of basically what we got when we compare the points between themselves. We see that, and I'll just use this to again highlight the quality of both sides. So we see that the general areas of interest and highlighted areas are pretty much the same, showing that even a lower quality 3D mesh is actually very useful and gives us the general information that we want to see. However, it doesn't really compare to the, higher quality mesh. Basically, what I'm saying is both are very useful for, basic 3D graphical analysis, but you probably want to use the more detailed version just to have a better idea of what's going on. Another thing that computer vision and computer programs allow us are far more accurate volumetric and data measurements. So as I mentioned, as you can see here, we took relatively accurate measurements of the point itself in all 3 dimensions. Now, why do I, bring this up? Well, if you were to, just talk about, how long or what the dimensions of this point were originally, you would probably be told it's around 15 and something centimeters, around 50 centimeters in width, and around 5 centimeters in width, and around 2 centimeters thick. And that's all fine, but when we use computer vision, we suddenly go from talking in centimeters to talking in micrometers. So, just kind of hammering in the point of what I said before, that computer vision gives us a lot more details than, simply using a ruler or just, traditional analysis. Just as a contrast, at the center here, we see the traditional technical line drawing, which is still present and popular in many archaeological circles, while both on the left and the right, we see a 3D, basically a visualization of the 3D model. As you can see, while the technical line drawing is incredibly detailed and highlights many of the key points of the actual point, it's still quite hard to compare to a computer-generated 3D model. Again, just as details, and it's also likely that 3D models take quite a bit less time and effort to make, provided you have the right hardware. So the final sort of, I suppose, result of 3D visualization, and potentially even to use it in augmented reality, would be what we see on the right. I'm sure many of you can imagine yourself putting on a VR headset and then analyzing this 3D model and all of its details, and that giving you, on one hand, a far better look into both the cracks and all the nooks and crannies of the point, while also, making it so the point can't actually be damaged, which is something archaeologists always have to worry about when working with physical artifacts. Just, another thing that I mentioned before, just to kind of, again, prove the point, is 3D printing, which 3D modeling makes it incredibly easy and quick. This is a 3D printed replica of the 3D point. And in case anyone was having trouble visualizing exactly how large 15 centimeters is, well, take out your pen. It's about that much. So, all right, now that we've gone through the basic points of data science, as well as the basic points of the wooden point, let's go over what exactly we did. So we predominantly used two open source systems to analyze the point. The predominant one being Cloud Compare, which we used for comparison and data analysis, as well as MeshLab, which we used to, sort of do an extra analysis just to make sure that all the data in Cloud Compare matched up with all the data from MeshLab, as well as used MeshLab to sort of check out if the dimensions were all the same. So, just to sort of make sure that there isn't any particular bias in one particular software. The general process that we used is that we took all 5 of the 3D models, we calculated their change of position, orientation, as well as the change of texture, and we use that to conduct a geometric, volumetric, and deformation analysis. To be more specific, instead of saying, okay, we just took 5 points, basically for each example, we took 2 points, we put them side by side, and we aligned them one on top of each other using an ICP, or iterative closest point algorithm, which we then, and after that, we used a algorithm. Well, Cloud Compare offers a set of algorithms to basically compare both the meshes. Now, Cloud Compare as a software offers a cloud-to-cloud, a cloud-to-mesh, and a mesh-to-cloud comparison. So whichever combination you want to put in it, it will work. No issue in that regard. On the right, we also see the general trend the point underwent during the conservation process. So just to quickly summarize, red means bending, orange and yellow are usually light swelling, while green and blue are varying amounts of shrinkage, as you can see indicated by the numbers. Now, let's first go over our case study of the 5 surface 3D models. As I showed before, this is the volumetric data that we were able to get out of the points. So 15 centimeters in length, 2 centimeters in width, 2 centimeters in depth, and 5 centimeters in width. And then we compared it. Basically, we compared these dimensions as well as the calculated volume from all of these models. And we basically see by the numbers here that there are, quite drastic changes since the beginning towards the end. Initially, a slight rise in all 3 dimensions, and then a considerable shrinkage in all 3 dimensions. So here's just another table with percentage basically calculations, but it basically just says what I said before, and I'll get into the details. We see that the 2 largest changes are with the thickness and the volume of the point, while the length and width have slightly less defined deviations, but still relatively noticeable. So less, but you can still see them quite easily. We decided to basically compare all the models with each other, which was a bit of a, I suppose you could say, perhaps slightly inefficient, but oh well. For this presentation, I'll be showing you predominantly all of the 3D models in comparison to the original 2009 3D model. So here we have the 2009 one. Now, if we go to the second scan, this was right before the process of conservation and was taken in Mainz, Germany. We see swelling in pretty much all areas, but the swelling is relatively minimal, a bit larger, as I said, in the thickness category, but less so in both width and length. The reason for this, in case anyone was curious, is because the conservation process with melamine resin, before they actually did the process of conservation, the point needed to basically be soaked in a distilled watery solution, which was absorbed by the point, kind of like a sponge, causing these volumetric changes. So, that was according to plan, but unfortunately, the subsequent shrinkage after the conservation process was a bit larger than I suppose many researchers had anticipated. So as we see predominantly in the central area, a large amount of shrinkage, and the tail point was a bit more bent. These basically differences only further I suppose, went on during the 2015 to 2017 process of the point itself drying. And here we have the 2018 model showing us also a set of quite a bit of deviation in the upper part, which we couldn't see before, showing that this part has also bent for some reason. So if we just go through it again, we see a slight amount of swelling, and then procedurally the point went shrinking after and as well as during the actual conservation process. So here's just another example. Take it from up to down. You basically have the red line, just so you know, is basically 0. That's kind of what we would want to all of the points to be at 0, but obviously that's not exactly going to happen. So we see that the first point, as I mentioned before, relatively minimal differences, but pretty much swelling in all dimensions. The second one, still some leftover swelling from the previous point, but a lot more shrinkage. Same thing with the next model, and finally the final model has very little leftover swelling, but much more shrinkage. So as I said, the trend continues. However, I would like to give a piece of good news, since what I was talking about up till now seemed pretty grim, right? The piece of good news is that it seems that the latest model, which was done in 2019, seems to be pretty much uniform with the 2018 model, showing that the points seem to have calmed down, at least as far as deformation is concerned. As I said before, we want as many points as possible to be at 0 and as few as possible to be towards the edges. So this is almost an ideal graph of what we would like to see in this regard. This also shows us that an artifact isn't simply done being conserved after the actual conservation process, but will most likely still require, a year or two to properly settle down into its final form. So again, just another type of visualization of the data that we have. And again, just as kind of a contrast, here we have the 2019 model in comparison to 2013. So we see mainly the upper side and bottom central part of the point shrinking and bending, while the 2019 to 18 is relatively uniform. It's ideally at around 0. The only places that seem to still contain some slightly larger deviations, I guess you could say, is the tip and the bottom tail point. So this basically just summarizes what I already told you. And here is a perhaps slightly more graphic depiction of how much the point actually shrunk. So this is a comparison between 2015 to 18, just, as a comparison. And here is the 2019 to 18 comparison in comparison with 19 to 13, and from all 4 sides of the point, we see that pretty much all of the previous swelling and shrinkage has more or less settled down, which is good. These are the only, as I mentioned, these are the only 2 points that still seem to show some greater deviation, and this also shows us. So here's the thing. The surface 3D models actually showed us that the 2 critical points would be the upper and lower part. The upper being for its shrinkage, and the lower part, we see that it actually hasn't shrunk at all. It's just bent. So a difference of position, while the central parts seem to be relatively uniform, right? Quite, overall, quite nicely done. But is that actually true? And I'm sure you can all guess why, since I'm bringing it up. But we wanted to figure out why exactly there was still some deviation in the upper and lower parts of the point. So we figured, well, if it's not external, then it might be internal. Unfortunately, surface 3D models do not give us that information. So we decided to, I suppose you could say, create our own. Thanks to the CT images that we were provided together with the 2018 as well as the 2019 3D models, which were done using a micro CT scanner, we basically needed to create a program which we could then use to create our own 3D models or point clouds that would also highlight the internal structure, not just the external structure. The solution that we came up with was an iterative segmentation algorithm that created a 3D volumetric model from approximately 3,000 2D microtomographic images, the overall quality being around one version being 1,000 times 1,000 pixels, the other being 3,000 times 3,000. But that's neither here or there. So here's just a quick graphical representation. We take the images created by the CT scanner. We run them through our program, which I should mention was written using the software tool MATLAB. We then convert the 2D points to 3D voxels. And then we basically paste all of these slices together to get the final 3D model that we want to analyze. During the actual process, we ended up creating two versions of the algorithm, one being a direct and one being a segmented algorithm. The main difference being that the direct algorithm just takes the point, thresholds the basically the pixels that we want in our 3D model and the ones we don't, and then converts them to voxels, while the segmented 3D model basically gives us an outline of both the external as well as the internal structure, and then creates a 3D model based on those. Why is that important? Well, firstly, the direct algorithm, while seemingly simpler, actually presents us with a larger number of issues, not so much with the algorithm, but with the results. Firstly, the results that you get are, I suppose you could argue, kind of a filled in point, which is all fine and well. It is what we wanted, but it's still much harder to actually, see inside the point, because the cracks and fractures and pores that are in there aren't, nearly as big as you would imagine, which is why when you actually use a direct model, it's much harder to see inside it than we initially thought. The bigger issues, however, were both the time that the algorithm spent on the direct algorithm, as well as the size of the files. So, for example, for the 2019 3D model, the direct algorithm created a 3D model about the size of, how much was it? Around 16 gigabytes, around over 10 gigabytes. So yeah, good luck. So, fun stuff, I suppose. On the other hand, the segmented algorithm posed no such issues. It went much quicker, and it also gave us far more manageable sized models than the direct one. The other thing, which I think is also far more useful with the segmented algorithm, is that it already highlights the parts that we want to see. So it highlights the internal fractures, the internal pores, air bubbles. Anything in there is already highlighted. You don't have to, sort of look at it from the right angle to see it. As I mentioned, both algorithms are done using the package for numerical analysis software tool, as well as the programming language known as MATLAB. So, as I mentioned before, the point of the volumetrical model is to give us these, I suppose you could say, holes, cracks, air pockets, pretty much anything that's darker in the point, and highlight them so that we can then analyze whether the internal structure has changed and how that affected the external structure. So as we see, these are all the images one after the other in a video. This is what we then decided to convert into a proper 3D model, as I showed you before. Here we have basically the same thing, just from a different angle, right? As we can see, most of the point is relatively whole, but there are quite a few cracks and empty spaces that we want to worry about. And because, a video might not give us quite as much information as we wanted, we decided to make a 3D model out of it. And let's just go over what that gave us. As I said, originally, we were worried that the top and bottom of the point were, in danger, or I suppose I should say critical elements that we needed to watch out for. Turns out the volumetric models pointed to exactly the opposite. Instead of the upper and lower point being the issue, the upper and lower point are actually the most, whole parts of the entire point. They have the least fractures, the least cracks, and the least issues, while the largest number of issues we have in the central part, as well as the central upper and central lower part of the point. So, for example, here we have one crack extending downwards and one extending upwards. from what it looks like, they won't actually connect with each other. But if they did, that would be a problem. So just putting that out there. So that was kind of the difference between volumetric data and typical surface data, and I believe it illustrates the point that we need more volumetric data if we're gonna analyze archaeological artifacts, especially ones that could have internal fractures, internal damages, etc. Now, I've already gone through what our research and data processing has highlighted, as well as what changes they are. I would also like to point out that based on what we've shown, the Cloud Compare software tool that I mentioned is very much an appropriate tool for accurately determining the dimensions of an artifact, its volume, as well as the texture, the volumetric measurements and their basic statistical treatment, the graphical processing and comparison of a point cloud or a triangulation network of 3D model artifact points, as well as the comparison of 2 or more 3D models and their data to perform the deformation monitoring that I mentioned before. I would like to conclude this presentation with 2 axioms. Firstly, there is no effective and successful treatment and protection of cultural heritage without an interdisciplinary approach or without standardized use of new technologies. The second axiom is 3D models as a form of digital heritage are today's need and tomorrow's necessity for the permanent as well as integrated preservation, evaluation, and presentation of tangible cultural heritage. As Francois Gingignan said, the 21st century archaeologists are no longer excavators. They integrate other disciplines such as history, epigraphy, geography, anthropology, ethnology, economy, agronomy, physics, chemistry, mathematics, computer science, and as we can see from this presentation, I would hope so, data science as well. Thank you all for your attention. All of our research and findings were published in this literature, all of which is accessible via the internet. So if anyone is interested, it's there. Thank you all for your attention.